youngster working on the nuclear power station is my friend Larry. He wants to be a scientist someday. I'm Dr. Woodley. I'm a scientist. I like Larry and answer his questions about atomic energy. I teach youngsters on scientific subjects. I was writing a book on atoms and the particles of matter the last time I spoke to Larry. Now Larry was visiting a science book on controlling the atom. Well, Larry, what do you remember from our talk the other day?
I know that everything around us that we see and touch is made up of billions of tiny invisible particles called atoms. Atoms are so small that lined up end to end would only inch, and the atom is made up of still smaller parts. There are neutrons and protons in the nucleus, and electrons which whirl around the nucleus in various orbits. But each atom is mostly empty space.
Very good, Larry.
I want to know about your new book, Dr. Woodley. What are radioactive atoms?
Well, scientists once believed that atoms of elements never change. Later, they discovered they were mistaken. We know that certain elements do change. They are naturally radioactive. This means that they give off a stream of energy in the form of powerful rays or particles shot out like bullets at tremendous speed. Radium is one element that is naturally radioactive. Radioactive atoms eventually lose their power, change into different elements during a period ranging from a fraction of a second to 10 billion years, depending on the element.
Can scientists measure this radioactivity?
Yes, Larry, they can. Let me show you with my watch. Scientists use Geiger counters to detect radiation. The Geiger counter measures the number of particles given off by the radium on the face of the watch. You can't smell them, taste them, or actually see them, but you can hear their effect. Working with strongly radioactive materials can be dangerous. It requires very special arrangements. This is a glove box. Here, scientists are protected by thick windows and walls. Machines using radioactive materials are heavily shielded with lead and concrete. In addition to radium, there are other naturally radioactive elements such as uranium. Uranium is the most complex atom found in nature. The most common type of uranium is uranium-238, with 92 electrons, 92 protons, and 146 neutrons. Scientists experimented to learn what would happen if they fired a neutron bullet at the nucleus of the uranium atom. What they discovered helped them develop a method of freeing and controlling some of the tremendous energy locked in the atomic nucleus. This power, atomic energy, has many uses to make a better world for all mankind. Think of it, Larry. The energy packed in a piece of uranium the size of this marble could drive hundreds of locomotives traveling at more than a mile a minute for more than an hour. Scientists release some of this energy through a process called nuclear fission. When a high-speed neutron strikes a uranium nucleus, the nucleus splits apart violently. A tremendous amount of energy is released in the form of heat and radiation. Extra neutrons are given off, and they serve as bullets which in turn strike other nuclei and split them too. The process is repeated. In a fraction of a second, billions of atoms are split in an explosive chain reaction, releasing enormous energy. An atomic bomb burst is a chain reaction out of control, creating millions of degrees of heat in only 10 millionths of a second. But a chain reaction can be controlled. The tremendous energy from the atom can be harnessed for man to use. This is done in nuclear reactors, sometimes known as an atomic pile, where a special type of uranium, uranium-235, supplies the neutrons for the controlled chain reaction. One type of atomic pile consists of a large cube of graphite with uranium rods inserted into holes in the graphite. The uranium serves as a fuel supplying the neutrons. The controlled chain reaction produces heat and radiation. If the uranium neutrons in a reactor were allowed to speed around naturally, they would be too fast to hit enough uranium nuclei. There would be no chain reaction. But a moderator, like water or graphite, slows the neutrons and encourages the chain reaction. The chain reaction in the reactor is under full control at all times. If the reaction is too strong, control rods, which absorb neutrons, move in to slow down the reaction. In this way, nuclear fission can be speeded up or slowed down at man's will. Nuclear reactors come in various types. Here you see what are called tank types. This is a uranium graphite pile. This reactor uses water as a moderator. It's called a pool-type reactor. I explained to Larry that a reactor cannot explode like a bomb. Then we discussed how the power from a reactor can be used. In a nuclear power plant, for example, electricity can be produced. The heat is generated in the core where the atomic fuel is located. It passes to a heat exchanger to make steam. The steam drives a turbo generator for the production of electricity. The source of heat is the only difference from a conventional power plant. A little bit of atomic fuel can do the work of thousands of tons of coal or tremendous quantities of oil. This new source of energy will help us save coal for other important uses. Electricity is already produced in nuclear power stations all over the country. Scientists are working to learn ways to make the cost of electricity the same price or lower than electricity from coal-burning plants. In a submarine, reactor heat can drive a turbine to spin the propeller. Atomic submarines can travel long distances without refueling. The famed Nautilus went under the North Pole, and the Triton went around the world completely submerged. The nuclear ship Savannah is the pioneer of the atomic-powered merchant fleet of the future. More cargo carried, much faster. Nuclear reactors have other vital uses. Substances not normally radioactive can be made radioactive in a reactor. We call these new radioactive materials radioisotopes. They play a big part in our world. They are used by doctors to diagnose and treat disease. They are used to sterilize food and drugs. And in research to improve the growth of plants and animals. Radioisotopes make possible gauges which measure the thickness of material automatically. Oil flow can be traced in pipelines. Wells are checked for strength quickly and efficiently. All adding up to better products and healthier lives for all of us. That's what will be in the book, Larry. All that, plus the idea we are only in the beginning. Young people will grow up to see the radioactive atom put to uses that have not yet been thought of.